Hi, this is Professor Fernandez, and in this video, we're going to work through examples on L'Hopital's rule. So these examples come from Lesson 9 in this Calculus 2 course. You can download the lesson notes at this website, where you'll find a bunch of other stuff as well. So let me go ahead and start talking about the example. So one thing I want to mention is that I want to just talk really quickly about L'Hopital's rule, why it exists, how we use it, and when we might not want to use it. So I'm going to scroll, zoom in over here on the right-hand side. I'm just going to leave this up for a minute. Maybe you can pause the video to read through it, but I'm actually going to give you a quick little introduction up here. So for example, what if we wanted to find the limit as x goes to infinity of x over x? You might remember from Calculus 1 that one of the first things we do is we try to plug in the c value. Whatever thing is here is the c value. So we might say, oh, this equals infinity over infinity. The problem is that infinity is not a number, infinity is more of a concept, so it doesn't obey the usual arithmetical operations that we're used to, like you can't cancel this out and get 1, for example. So infinity over infinity is what's called an indeterminate form. That means that when you get this, quote unquote, get this for the answer of a limit, it's not really the final answer to the limit. There's something else you should be able to do to get that final answer. In this case, for example, so given that this is not the final answer, what could we do? Well, we could use L'Hopital's rule. We'll talk about that in a minute, but that's a bit too fancy for this application because, you might have already realized that you can just cancel the x's. So this is the same as the limit as x goes to infinity of the number 1, which is just 1. So the answer is indeed 1. So if you go back, though, and you try this new limit, right, how about 2x over x? Again, if you just try, substituting in, quote unquote, this, whatever is here, in this case, infinity, you get, once again, infinity over infinity. Doesn't tell us much. And if you go back and then say, all right, I'm going to do something else, and you try the same usual simplification we just did, you can cancel the x's. In this case, the limit as x goes to infinity of the function is 2. So, you can see what happened here, right? If I just erase all the things we did. In these two very different cases, we had the same intermediate results, which is infinity over infinity. Yet we got different answers, right? So this is one of the reasons why limits that yield, quote unquote, that tend to infinity over infinity are called indeterminate. You can't determine their value just from the fact that they tend to infinity over infinity, because they might have different values. And you can see that we can construct an example where I put in any number a times x over x. The answer is going to be a. At the same time, the answer is always infinity over infinity, right? As I convinced you, that's actually never the answer, but that's what, again, you might think as you start evaluating these limits. I could have gone back and replaced everything with limit as x goes to 0, and the exact same conclusions would have held, right? All of these would have, quote unquote, tended to 0 over 0, but they would have all had the exact same values that we found them to have, a, 2, and 1. So that's why when you get something like infinity over infinity or 0 over 0 for a limit, that's called an indeterminate form. So the whole point of L'Hopital's rule is to start with that premise. If the limit is indeterminate of type 0 over 0 or infinity over infinity, then L'Hopital's rule gives you another option, right? Notice that what we did up here is we did algebraic simplification to find the limit. And in fact, I really do stress that this is probably the first thing you should try to do. And I'll send you to video 5.2 in this playlist for a couple of examples, few examples of how you would use algebraic simplification to evaluate limits as x goes to infinity, for example. In other words, not using L'Hopital's rule. But if you are going to use L'Hopital's rule says, okay, if you have a limit that's 0 over 0, tending to 0 over 0, or infinity over infinity, then here's what you could do, right? The limit is equal to the limit of the ratio of the derivatives. Okay, so let me say that again another way. What you do is you take the derivative of the numerator, that's f prime, take the derivative of the denominator, that's g prime, divide them, and then take the limit. Right? In other words, you take the limit of the ratio of the derivatives. And that is equal to your original limit provided the limit on the right-hand side exists or yields plus or minus infinity. Right? So I need to edit that wording there a little bit. So if this right-hand side limit, declutter this for a second here, if this right-hand side limit exists, let's say it's a number like 7, then that's the original answer. That's the answer to your original limit. So that's great. Also, if this right-hand side number is something like tends to infinity, tends to minus infinity, then that's also the original answer to your limit. So that's what L'Hopital's rule tells us. Okay, so now let's go back and see a few examples of L'Hopital's rule, and also see, again, instances where you might not want to use L'Hopital's rule unless you're explicitly asked to do so. So here's the first example. Limit as x goes to 0 of e to the 3x minus 1 over x. The first thing to know about the L'Hopital's rule that I just read to you, there are other variants. We'll talk about that in the next video in this series. But the L'Hopital's rule I just read to you applies when the limit tends to 0 over 0 or infinity over infinity. Those two particular indeterminate forms. So if we're going to use L'Hopital's rule here, that's the first thing we have to check. That being said, I would try, this being evaluating limits, try the advice that you got in Calculus 1 to begin with, which is just substitute in the c value. In this case, c is 0. So we get e to the 3 times 0 minus 1 over 0. That would be e to the 0 minus 1 over 0, which is 1 minus 1 over 0, which is 0 over 0. There is our telltale sign that we have to do something different. 0 over 0 is never the answer to a limit. Okay, so we have to do something different. So now I would recommend going back to look at the function and see if there's any algebraic simplification you can do. In other words, avoiding L'Hopital's rule. I wouldn't say I have a bias against L'Hopital's rule, but I would say that because it requires differentiation, it's a personal preference, right? If you can avoid L'Hopital's rule, you avoid differentiation. If you're really good at differentiation, you might want to try L'Hopital's rule. But again, as I said, L'Hopital's rule that I read to you, the limit has to be tending to 0 over 0 or infinity over infinity, so that's another constraint. There's not really anything we can do algebraically here to simplify this function. So the limit does tend to one of the indeterminate forms that L'Hopital's rule treats. So we are going to go ahead and apply L'Hopital's rule. To do that, we're going to write out the original limit. And then notice that the numerator is e to the 3x minus 1. So we're going to take its derivative, right? And this new limit is going to equal the value of the limit we're trying to find, the original one, provided the new limit actually tends to a number, or it tends to infinity or negative infinity. Okay, so here I am writing what's going on, and then let's do these calculations here. So I have to remember some derivative facts now. These were covered in Calculus 1. You can find a playlist, a few videos in the playlist for Calculus 1 for my course. So if I differentiate here, derivative of e to the 3x, that's a chain rule. It's e to the 3x multiplied by 3. And then derivative of 1, that's a constant, that's 0. And then down here, derivative of x, that's the power rule, so that's just 1. Okay, so I'm left evaluating the limit of 3e to the 3x. Divided by 1, I won't write that. So this one is fairly simple, right? We try the same thing we try normally, which is substituting in the value x is tending to, the c value I keep calling it. And this just gives us 3. So there we go. So we got a number, and that is therefore the answer to our original limit via L'Hopital's rule. So that's pretty nice. So that's part A. Okay, you can see that I started off with a fairly straightforward example in the sense of you only had to apply L'Hopital's rule once. So that's kind of a hint that you may have to apply L'Hopital's rule multiple times. We'll see that in part C. Okay, let's look at part B here. Limit as x goes to infinity now of ln of x squared over x. Notice that, again, algebraic simplification goes a long way. We don't have to do it here, but we could, and I would argue we should, because it simplifies the problem, right? Makes it easier. You might remember rules of exponents, right? That ln of a to the b, you bring down the b and multiply it by ln of a. So I'm going to use that here. So I'm going to bring down the 2. So this is 2 ln of x divided by x. And then properties of limits, I can bring out the 2. There we go, ln of x over x. So this is a simpler limit to tackle now, which is what I'm going to do here. So let's try the usual. So what if I plug in, quote unquote, infinity, right? I'm going to end up with ln of infinity over infinity. So that's infinity over infinity, another indeterminate form. So L'Hopital's rule is on deck. It is definitely something we could apply, but ask yourself, is there another way to simplify this, right? Might be faster to do the limit that way. Answer, not really. There's nothing here we could do. We can't rationalize, we can't, find a common denominator, some of the things you might have done back in Calculus 1. So we're going to go ahead and apply L'Hopital's rule. So this is going to equal 2 times the limit as x goes to infinity of the ratio of the derivatives. Okay. It's really important to keep that in mind. This is a ratio of the derivatives. One common mistake is to differentiate this function, right? Using, in this case, the quotient rule. You don't want to do that because that's not what L'Hopital's rule says. L'Hopital's rule says ratio of the derivatives. Okay? All right, so here we are, ratio of the derivatives. And what do we get? Let's see. So 2 limit as x goes to infinity of the derivative of ln of x, that's 1 over x. The derivative of x, that's 1. So actually, we're just left with the limit as x goes to infinity of 1 over x. And we've definitely dealt with that limit before in Calc 1, so that limit is 0. So 2 times 0 equals 0, so that's the value of our limit. Okay, great. So we've gotten 2 nice applications of L'Hopital's rule. Not much seems to have changed. Initially, we started off with a limit. We couldn't simplify algebraically or very minimally in this case. And then we applied L'Hopital's rule once, and it worked. Okay, let's look at example C now. And this will be the one that's slightly different. So what if x tends to infinity and we're dealing with x squared over e to the x? Again, if you try just substituting, you would get infinity squared over e to the infinity. That's basically infinity over infinity. Another indeterminate form. So cue L'Hopital's rule once again. You can't really algebraically simplify that. So hence L'Hopital's rule is the only game in town. So equals the limit as x goes to infinity of the derivative of the numerator over the derivative of the denominator. And then what am I going to do with this here? Okay, derivative of x squared is 2x. Derivative of e to the x is itself. And we're like, now I'm going to try substituting in infinity again, right? I'm going to get 2 times infinity over e to the infinity. Hey, I get infinity over infinity again. I did not get a number like in the other 2 examples, right? I got another indeterminate form. So at this point, you might be thinking, did we do something wrong? And the answer is no. What happened is that you started with a limit, which yielded an indeterminate form. You applied L'Hopital's rule. You got a new limit, which again yields an indeterminate form. So look at that like cycle. We now have a limit that yields an indeterminate form. So guess what? We're going to apply L'Hopital's rule again. That's right. You can do it more than once. So the value of this limit is going to equal the limit as x goes to infinity of the derivative of the numerator, L'Hopital's rule, divided by the derivative of the denominator. And then let's work this out here. So what if I differentiate the numerator, derivative of 2x, that's 2, differentiate e to the x, again as itself, and we again reattempt to take the limit, evaluate the limit again. In this case, we're more successful because 2 stays 2, but the denominator goes off to infinity. So this gives us 0. So now follow, this is why I've been very careful to use equality signs where appropriate. So 0 is the answer to this limit, which equals this limit, which equals the original limit we started with. In other words, the original limit we started with equals 0, right? So quick little takeaway here, right? In the first 2 examples, we applied L'Hopital's rule once, worked out. The last one we had to apply L'Hopital's rule twice. So that's one thing, again, to take away from this video. Not just what an indeterminate form is. We talked about that in the beginning, how to spot them. There will be other indeterminate forms I'll talk about in the video down here, as you can see. But for this video, 0 over 0 and infinity over infinity are the basic indeterminate forms. They show up a lot in calculus. When you have a limit that yields one of these 2, then you can apply L'Hopital's rule. And L'Hopital's rule tells you the limit equals the limit of the ratio of the derivatives, right? So that was down here. And then you might have to apply it once like we did over here. And before you do any of that, I would definitely recommend algebraic simplification. It'll make your life easier, and you might even avoid having to take derivatives and apply L'Hopital's rule. All right, thanks for watching.